When we picture offshore energy, we almost always think of those massive platforms or the vast drill ships out on the horizon. But the true control center, the literal brain that dictates whether a well is safely contained or actively producing, sits right there on top of the wellhead. Today, we're going entirely under the hood in this explainer to look at what the industry calls the Christmas tree. We've got a great lineup for today. We'll be covering the brain of the anatomy of a vertical tree, the incredible downhole safety failsafe, the evolution into horizontal trees, and finally, how we handle precision subsea installations. Let's get right into it. Starting off with the brain of the well, and what is up with that name? Before we get into the heavy engineering, the extreme pressures, and the deep water robotics, we really need to address the elephant in the room regarding this strangely festive terminology. I mean, it's a completely fair question. Why on earth is a massive block of high-pressure, incredibly serious industrial steel officially called a Christmas tree? It sounds like an inside joke, right? But the name has stuck for decades, and it's the actual technical term used by engineers all over the globe. It all goes back to the wild early days of the oil industry. The chaotic collection of valves, fittings, and pressure gauges that they used to just pile high on top of a wellhead was said to vaguely resemble a decorated Christmas tree with all its ornaments sticking out. Now, modern trees are sleek, incredibly compact, and totally computer-controlled, but they still serve that exact fundamental purpose, acting as the absolute primary control point for the entire well. Just look at a real-world modern surface tree on a gas rig. Standing as the main isolation valve assembly, this is the exact choke point through which wet gas at full reservoir pressure has to pass before entering the production flow line. And we're talking about pressures anywhere from 2 to 3,000 psi. It's a seriously formidable piece of hardware. Moving on to vertical tree anatomy, let's build this from the bottom up. We really need to break down a conventional vertical tree from the wellhead upward to truly understand how its anatomy works. Now, what's fascinating about this is the solid forged steel block body. Unlike older onshore trees that might just be individual valves bolted together, this solid block design is highly preferred for offshore service. Machining the valve bores directly into a single massive forging practically eliminates potential leak paths. And when you're dealing with high-pressure, highly corrosive fluids over the open ocean, eliminating any place a leak could start is rule number one. So let's build the tree upwards and see how this brain is organized. Starting right at the bottom, you have the lower master valve, which is your primary isolation point. Right above that is the upper master valve, giving you a vital redundant barrier. From there, the flow takes a 90-degree turnout through the wing valve to head towards the processing facilities. Next in line is the choke, which basically restricts and regulates that massive pressure coming out of the ground. And finally, sitting right at the very top, is the swab valve. That one stays normally closed, but provides a straight vertical access path when engineers need to lower wireline tools directly into the well. By comparing the exterior solid block to the internal schematic, you can perfectly visualize how these hydrocarbons are managed. The flow blasts up from the bottom, passes right through those two master valves, and then is directed sideways out the wing valve. All the while, the swab valve at the top stays tightly sealed up. It's just an incredibly elegant and robust way to route such extreme, violent pressure. Now let's talk about the downhole safety failsafe, the SCSSV. Because the tree doesn't just control the flow right there at the surface, it actually orchestrates the well's ultimate emergency reflex deep, deep underground. This brings us to what might literally be the most important safety device in the entire offshore industry, the Surface-Controlled Subsurface Safety Valve, or SCSSV. The Christmas tree acts as the hydraulic control interface for this valve. A hydraulic control line runs straight from the tree body, down through the wellhead, and actively sends pressure thousands of feet down the well to hold this critical safety barrier wide open. The absolute most crucial point here is the fail-safe principle. There's a massive spring inside that SCSV that desperately wants to slam a heavy metal flopper shut to block the pipe. The only thing stopping it is that hydraulic pressure being pushed down from the Christmas tree on the surface. If that tree gets damaged, say by a ship's anchor or an extreme collision, that hydraulic line gets severed. The pressure instantly drops to zero, and that heavy spring automatically snaps the flopper shut, completely sealing the well without a single human needing to hit a button. And to put that into perspective, this safe is located 60 to 90 meters below the seabed. By burying it that deep, the barrier remains entirely safe from virtually any catastrophic event happening up on the surface. You could literally shear the entire top of the well off, and the ocean is still protected. Next, let's explore the horizontal tree evolution, which was a massive paradigm shift. As the industry moved into deeper and much more hostile waters, the traditional vertical anatomy we just looked at really had to evolve to meet some brutal physical and economic realities. Check out this stark contrast. With a traditional vertical tree, if you need to pull the tubing out of the well for a major repair, you have to completely remove the massive Christmas tree first. It is incredibly expensive and risky. But a horizontal tree features a wide-open, through-bore design. That means you can actually install or remove all the inner well equipment straight through the tree itself, without ever having to unbolt the tree from the wellhead. When you look at the cross-section of a horizontal spool tree, you notice how the main vertical path right in the center is completely clear of valves. Instead, the production bore runs horizontally straight out the side of the main body. The master and wing valves are mounted externally on the side. The vertical path is then just sealed at the top by a heavy-duty tree cap until it's ready to produce. This evolutionary leak drastically reduces the cost and risk of maintenance. It is absolutely vital for subsea wells that rely on electrical submersible pumps, or ESPs, to boost pressure in aging oil fields. Those pumps eventually wear out. With a vertical tree, pulling a dead pump could cost millions just to mobilize a ring to remove the tree. But with a horizontal tree, you just leave the brain perfectly in place, pop off the top cap, and pull the pump straight out. It's a total game changer. Finally, let's get into precision subsea installation, operating in the deep. Knowing how these massive blocks of steel work on a whiteboard is one thing, but actually installing them on the dark, freezing ocean floor requires unbelievable precision. And it's all done without a single human diver. These subsea trees have to be landed, aligned flawlessly, and locked into place at depths where the crushing water pressure would be instantly fatal to a human. The tree is meticulously put together and tested up on the surface rig and then lowered slowly to the seabed on a drill string. It's an incredibly delicate, high-stakes operation. The true unsung hero of this entire process is the tree running tool, or TRT. Think of it as the ultimate delivery vehicle. The TRT grips the Christmas tree, lowers it through the water column, lands it perfectly onto the subsea wellhead, and then triggers a heavy hydraulic latch mechanism to secure it. Once that tree is locked tight, the TRT safely detaches and is pulled right back up to the surface. The connection itself is a marvel. You have the heavy-duty subsea wellhead structure mating with the hydraulically operated tree connector. When hydraulic pressure is applied to the heavy clamp segments, they bite down incredibly hard, locking the whole system firmly in place so it can withstand the immense reservoir pressures that are actively trying to push the tree right off the well. Once the tree is physically bolted down, it needs to be plugged in. Robotic submarines, known as ROVs, swim in to connect what we call the flying leads. These are the critical umbilical jumper cables that provide electrical power, data telemetry, and hydraulic fluid to the tree. Once the ROV plugs these in, the well's brain is officially connected to the host facility miles away, giving operators full remote control. It honestly is incredible to realize the sheer scale, precision, and ingenuity of the offshore engineering that quietly and safely powers our modern world. So as you go about your day and use energy today, whether turning on a light or filling up your car, consider this. What other invisible, monumental engineering marvels are operating flawlessly thousands of meters underwater right now, completely out of sight? Thanks for joining me on this explainer. Keep learning, and I'll see you in the next one.